video is a discussion of the conservation of linear momentum. And what this basically says is that during a collision or explosion, momentum is conserved. So the total momentum of any objects before an event happens, like a collision or explosion, is equal to the momentum after that collision or explosion. So what the problem-solving technique they're going to use here is to look at all the objects, see what the momentum is of all those objects before, and set that equal to the momentum of all the objects afterwards. And the equation is exactly that: initial momentum equals final momentum. The total linear momentum at some initial time ti will equal the total linear momentum at some later time tf. So I'm going to do an example here. We're going to take a look at how to approach one of these problems. We have a 55 kilogram swimmer is standing on a stationary 210 kilogram floating raft. The swimmer then runs off the raft horizontally with a velocity of 4.6 meters per second relative to the shore. Find the recoil velocity that the raft would have if there were no friction and resistance due to the water. So this is considered an explosion, and we're going to go ahead and say the initial momentum equals the final momentum. And once we have that in place, we're going to look at, well, what is the initial momentum? Well, originally the momentum was zero. The swimmer and the raft are at rest. And then when they explode apart from each other, there's now two objects. And so we're going to look at the momentum of each of those. And one's going to the left, one's going to the right. So that means that one has a negative momentum. So here's our picture where we initially have zero momentum, and then we have these two things going apart from each other, and we have to now use our equation, and I'll show you how that works. Since the initial momentum is zero, that's what we put right here, that's our initial momentum is zero, and we have the units are 0 kilogram meters per second equals, now we have the momentum of the raft, and that's going to be a negative momentum, plus the momentum of the swimmer. Now those two momentums have to be equal to each other. If we add this momentum over to the other side, we end up with momentum from the raft equals the momentum of the swimmer. And what we do now is we say mass times velocity of the raft equals mass times velocity of the swimmer. We go ahead and plug our values in now. We know the mass of the raft is 210 kilograms. The velocity of the raft is what I want to solve for. The mass of the swimmer is 55 kilograms. The velocity of the swimmer is 4.6 meters per second. Now we go ahead and solve for the velocity of the raft. We end up with an answer of 1.2. That ends up being 1.2 meters per second. A different kind of problem we're going to run into is something like this one. It says a 0.15 kilogram projectile is fired with a velocity of 715 meters per second at a 2 kilogram wooden block that rests on a frictionless table. The velocity of the block immediately after the projectile passes through it is 40 meters per second. Find the velocity with which the projectile exits from the block. So this first section here is the initial section. It's where the projectile is coming at 715 meters per second. Is in this block here is 2 kilograms is 0 meters per second. And then after the projectile passes through the block, this is the final section where the projectile literally has come through the block here and come out the other side. So we have initial momentum equals final momentum. Initially, this block here has zero momentum, so the only thing that has momentum is this bullet here. So we're going to say, or a projectile they call it, so we're going to say mass times velocity of the projectile, and we'll set this up. And you can say mass times velocity of the block. We'll do that there. but that's just going to be 0, equals mass times velocity of the projectile plus mass times velocity of the block. Now, what a lot of times, what you'll see in textbooks and so on is they'll put primes here just to remind us that it's the after, the final position. So you go ahead and plug in your values. The mass of the projectile is 0.15 kilograms. The velocity of the projectile is 715 meters per second. Now I'll go ahead and just plug out, and that's 715 meters per second. This next term goes to 0 because the velocity of the block was 0, equals the mass of the projectile has not changed. It's stated as 0.15 kilograms. The velocity of that projectile is what I want to solve for. That's what we're trying to find. Plus, the mass of the block stayed 2 kilograms. We're assuming we didn't lose any of that block after the projectile passed through it. And the velocity of that block is 40 meters per second. So we'll go ahead and put there. Now we just go ahead and do our calculation, and we find the velocity of our projectile to be right around 182 meters per second is the velocity of that bullet afterwards. The next section we're going to look at here is called momentum and kinetic energy in collisions. Now, momentum is always conserved in a collision, but kinetic energy is not always conserved. As a matter of fact, it never is conserved unless the closest it comes to is at subatomic particles that you may have kinetic energy conserved. But it's like frictionless surfaces. You do talk about kinetic energy being conserved, as well as you talk about frictionless surfaces, even though they don't exist. It's something to look at. And if kinetic energy is conserved, it's called an elastic collision. So I'll just go ahead and read this paragraph. It says, if the kinetic energy of a system is conserved, it is the same before and after the collision. Such a collision is called an elastic collision. In everyday collisions of common bodies, such as two cars or a ball and a bat, some energy is always transferred from kinetic energy to other forms of energy, such as thermal energy or energy of sound. Thus, the kinetic energy of the system is not conserved. Such a collision is called an inelastic collision. So all collisions basically are inelastic, unless told otherwise. Now, a perfectly inelastic collision is a collision where the two objects stick together. So that's called perfectly inelastic. So you have three types: elastic collisions, where both momentum and kinetic energy is conserved; inelastic collisions, where only momentum is conserved; and perfectly inelastic is where momentum is conserved and the two objects stick together. So just a brief recap of elastic collisions in one dimension: total kinetic energy before the collision equals the total kinetic energy after the collision. In an elastic collision, the kinetic energy of each colliding body may change, but the total kinetic energy of the system does not change. So here are the three types of collisions. If you want to put this in your notebook, you can pause the video and write these down. Here's an example of a perfectly inelastic collision. And you'll notice that the velocity of 0.2 meters per second and 0 meters per second, so wagon 1 and wagon 2 have those velocities. See what happens to the velocities after they connect. After the collision, you can see down here that they go at 0.1 meters per second down here. Momentum was conserved. And if we look at an elastic collision, you'll see what we have here is that the kinetic energy is conserved both before and after. They don't stick together. If we look at the momentum vector, we'll see that the momentum vector does not change at all throughout the whole collision. Here's an example of a person jumping off a cart. If you look up here, you'll see the mass of the person is 50 kilograms. The velocity that they're going to jump off with is 2.5 meters per second. The mass of the car is 100 kilograms, and then we want to solve for the velocity that the cart goes off with. Initially, everybody's at the cart and the person's going 0, so the momentum beforehand is 0. See if you can calculate what the velocity of the cart is afterwards, knowing this, knowing that what the momentum is before and what the momentum has to be after has to be equal. The momentum beforehand is 0. See if you can calculate what the velocity of this cart has to be in order to make the momentum after 0. So pause the video and try that. And here's our answer. And they say here it's 1.3 meters per second, but it's actually, you should end up with an answer of 1.25 meters per second. Here's another interesting example. We have these astronauts out in space, and look what, and in order for this astronaut here on the right-hand side to get moving, what does this astronaut have to do? So pause the video, think about that, come up with an answer, and you'll see that the astronaut has to throw the ball back and forth, and we'll see what happens here when we hit play. You see the ball bouncing back and forth. Momentum is conserved with each collision, and these astronauts continue to move backwards. So what we've learned here is that momentum is conserved in all collisions. Kinetic energy is only conserved in that special case called elastic collision, but momentum is always conserved. So the momentum before equals the momentum after any collision or explosion. And these are the types of problems we'll be doing in class.